So please.
Okay, so thank you for having me here. Please stop me if you have any questions at any moment. This is based on the joint work with Martin Balázs and Timo Sepalainen. So I'll break this talk into three parts. The first part will be where I'll present the model that I'm mostly interested in, which is called the last passage percolation. I'll state also in that part, I'll state the problem that we're interested in and the result itself, a bit history and the result. Then in the second part, I'll try to give you a sketch of the proof and for last passage percolation. And lastly, in the third part, I'll discuss a closely related model called random polymers. I'll again state an analogous result and the problem and the result. Okay. So there's this black thing here. Just a second. Yeah, so the model is as follows. Imagine a z square as a graph, as the lattice, and to each vertex we assign exponential weight that is a positive weight that is exponentially distributed, and we take these weights to be IID. Okay, they're independent and they're all distributed in the same way across the lattice. Now you fix 2 points, let's say x and y, such that y is above and to the right of x, such in the picture. And then you ask, what is you look for a path starting from x, terminating at y, that takes only either right or upward steps on the lattice, starting from x and terminating at y, and that maximizes the weight along itself. Okay, so for example, here is such a path. This is an upright path going from x to y, and if it maximizes the weight along itself, namely it has the most weight along itself compared to other paths, upright paths, then we call this path a geodesic. We denote it by pi xy, and we denote by gxy the total weight, which I will call, excuse me, the passage time. Okay, so maybe it's worth mentioning here that even though, so when you talk about geodesics, you think about the shortest path between 2 points. So here it's just worth remembering that we're sort of maximizing the distance in a way. So we're looking for the maximizing path. Okay, so let me mention the most basic properties of last passage percolation, or LPP in short. So the first goes back to a result by Ross in 81, which is called the Shape Theorem, where imagine that for each, you look at the positive quadrant, and for each n positive natural number n, you look for all the points and all the vertices in the positive quadrant whose passage time from the origin to those points is less or equal than n. Okay, color it in purple. Then if you take n to infinity and you scale this set by n, such as I did here, then it turns out that this converges to a deterministic set. So, right, so for every n, you'd have sort of a random set, a random purple set of vertices, but it turns out that if you scale it and then you converge to a deterministic set, almost surely, that's given by this inequality. Now, this, you should think of this as a law of large numbers, okay? So now that we have the law of large numbers, we can, the next thing you usually do in probabilities, you look for the fluctuations. You look at the fluctuations. So let me denote by Gn, the passage time from the origin, from the point 0, 0 to the point nn, okay? This is on the diagonal and the point nn. So it turns out that so we know by the previous result that this thing, that the first order term of this object is 4n, right? And so if we subtract it the way we would do in the central limit theorem, then it turns out that the fluctuations are of order n to the 1/3, as opposed to n to the 1/2 for the central limit theorem. And then if you scale it by that order, this converges to the Tracy-Widom distribution. So this is a distribution that's prevalent in random matrix theory. Okay, so the third property is concerned with the geodesics themselves. So up to now, what we discussed is just the passage time, right? The time from one point to the weight you collect between 2 points. But what do the geodesic look like when you let the endpoints be far from one another? So, for example, so it turns out that if you take the endpoints, you take the distance between the endpoints to be of scale n, then these paths called geodesic concentrate along the characteristic line. The characteristic line is just a straight line connecting the 2 endpoints. And not only that, it turns out that it scales like n to the 2/3 around the straight line connecting the endpoints. Okay. So these are like the 3 most basic properties of this model. And let me try to sort of maybe discuss a bit just the context in which this model should be considered. So this model is a member of something called the KPZ universality class. And to understand what that means, this KPZ universality class, it's helpful to sort of recall what the Gaussian universality class is. So it's well known from basic probability courses that if you have the following conditions, such as fast mixing of the environment, that means like something like IID random variables, and they have finite variance, okay? Then you should observe the following properties for when you consider large sums of these random variables. So the first thing is the law of large numbers. Namely, if you look at the average ensemble, empirical ensemble, then this should converge almost surely to a deterministic number, which is the expectation of the variable itself, of the random variable. Then you have something called the central limit theorem, namely that the fluctuations are of order n to the 1/2, and if you scale it by that, if you subtract the first order coming from the law of large numbers and you scale by n to the 1/2, then you converge to something called the normal distribution, this well-known bell curve we're familiar with. And lastly, there's even something called the Donsker principle, which basically what it means is that if you consider the paths generated by summing over these random variables, this would look like this kind of erratic trajectory. And then if you scale it properly, then you converge to this kind of this random function called a Brownian motion. Now, the key thing, the reason why it's called the universality class is because the whole thing is independent of the distribution of the environment, right? So as long as you have finite variance and as long as you have these independence, then you should see these things, right? You should see this kind of behavior, and it's independent of the distribution itself. Okay, so what is the KPZ universality class? So the KPZ universality class is kind of a bunch of models that are supposed to model the behavior of random interface growth. What do I mean by that? So if you think of a coffee stain, the way it sort of grows around the paper, it sort of spreads around the paper, or you have, let's say, a bacteria, like a bacteria colony, the way it grows on a surface, or snow accumulating on a windshield, these should all have, or believed to have, the same sort of kind of a same fluctuation behavior. And what we assume here is that we have this kind of this whole thing is sort of drive by the dynamics is drive by a white noise, some like IID random variables, as you saw in the last passage percolation. You have, you should think of this as the independent snowflakes coming from the sky. This is like the white noise, and the dynamics is local in the sense that locally you don't care about the snowflakes falling away from your position. And then there's a smoothing dynamics. So if we have this kind of a deep valley in the surface, in the random surface, then this would fill up quickly. Okay? And the third one is that the growth is proportional to the square of the gradient. This is like the slope of the local slope of the interface. And if you have all of these, then again, independent of the environment, of this driving environment, you should see the following things. You should see a law of large numbers, as we saw for the last passage percolation. We should see a central limit theorem, but now the fluctuations are of order n to 1/3, and then we should also see a non-Gaussian limit distribution. And finally, we have this functional convergence, the way we had for the Gaussian universality class. We should have that, we have this kind of a functional convergence to these limiting processes. We have a few of them, to name a few, the Area 2 process, the KPZ fixed point, and the directed landscape. These, over the years, have been refined. And this is sort of the context in which this model lives, and the other model that I will talk about in the last part. Okay, so up till now, we discussed these geodesics between two points, right? You have two fixed points, and then you look for the geodesics between these 2 points. But then we can also talk about infinite geodesics. So infinite geodesics are just upright paths on Z square, and such that if you fix 2 points on these paths, then the path restricted into between the points is itself a geodesic. Okay, so this is very similar to geodesics and Riemannian manifolds. And what can we say about these infinite geodesics? So if you fix it, it turns out that if you fix a direction, okay, between 0 and half pi, then for every point, every point, let's say a point X, there exists a unique infinite geodesic emanating from X and going to infinity in the direction theta. Okay, and this has been proved for general weights actually. And what this means basically is that if you sort of have these, if you look at different points around X, then this would sort of generate this kind of an infinite tree. From every point you have a path going to infinity. They all coalesce as they go to infinity, and this sort of generates a tree. Okay, and what happens if we said that for every fixed direction we have this kind of a uniqueness, existence and uniqueness. But what happens if we look at the random direction? Then it turns out that in fact for every point X, if you take there is a random, the exceptional direction, theta 0, let's call it, where you have actually two infinite geodesics going in that direction. This is the message to take from this, is that basically what's true for fixed directions isn't, things get more complicated when you look at sort of random directions. Yeah, so this is something we'll see in what comes next. Okay, so we saw that for every point, we fix a point, then there's a unique, if we have a direction, then there's a unique geodesics emanating from that point into that direction. But do we have geodesics that are not rooted, that sort of by infinite, going, stretching into infinity in both directions? These are called bi infinite geodesics. And so yes, obviously there are. For example, the horizontal line. So we have, if you take a horizontal line, then this is clearly a bi infinite geodesic, because if you fix 2 points on a straight line, there's only one way, one directed way to go from point A to point B, only going to the right. And this means that this has to be a geodesic, a bi infinite geodesic. And the same reasoning goes to show, shows that the vertical lines are by infinite geodesics as well. But in a way, these by infinite geodesics are sort of trivial because, well, they're not that very interesting. And then the question can be refined into asking, are there non-trivial by infinite geodesics, which is the question I'll be most interested with. And this question is believed, so the legend has it that this was first asked by Hillel Furstenberg to Harry Keston, but in the context of first passage percolation. So first passage percolation is a close kin of the last passage percolation, as the name suggests. Basically, you again look on the z-square graph, but here you have these weights on the positive weights on the edges rather than the vertices. And given 2 points on the lattice, you ask for the shortest path going from A to the point B. And the distance is just the minimal path. And the reason why they were interested in the first place with these by infinite geodesics is coming from this another model from statistical mechanics called the Ising model, where you have on this, imagine on the z-squared that you have these kind of profiles called sigma, and for every sigma x, namely for the vertex x, it takes the value -1 or 1, and then you have these positive IID weights on the edges, and using this formula, you can sort of compute what we call energy of the, well, there's no minus, there shouldn't be minus here, but there's the energy of the profile. And then you look for ground states, namely states that these profiles that sort of minimize the the energy. So to cut a story short, long story short, we have, it turns out that if you do have a bi-infinite geodesics in the first passage percolation, such as this path here, let's say, then if you put all pluses on the left and all minuses on the right, then this is a ground state. Okay, so this is a sort of equivalent problem. And therefore, they were interested in understanding whether there are, so this is the main question in using statistical mechanics, whether the existence of ground states, and therefore the motivation came from there. Okay, so this is the question: are there non-trivial bi-infinite geodesics for first passage percolation and also last passage percolation? So the main progress in this field, essentially, and also in first passage percolation in general, came from Chuck Newman and his students back in the 90s. So the first result, maybe the relevant result, is by Latsier and Newman, where they show the non-existence of bi-infinite geodesics in a fixed direction. So if you fix a direction for first passage percolation, there is, they show that there's no bi-infinite geodesic outside this kind of a zero Lebesgue measure of directions. This was then strengthened by Alberg and Hoffman and Damon and Hansen, where they showed the same result, only they sort of showed it for every direction other than sort of outside the set of zero Lebesgue measure. This was then proven for general weights by Giorgio Thulaga and Seppäläinen for last passage percolation in a fixed direction. So again, you can see that what is it's one thing to prove for a fixed direction, but then when you go sort of where you can have a sort of a random direction, which is basically the problem, this becomes harder. But then in 2019, this was finally proved for last passage percolation, for exponential last passage percolation by Basu, Hoffman, and Sly. And a few months later, using different techniques, with Marton Balázs and Timo Seppäläinen, we showed the same result. And a year later, with Timo, we showed an analogous result for another interesting model in the KP's universality class called the low gamma polymer. Okay, so now we come to the second part of the talk, where I'll try to give you sort of a sketch of the proof. So since the model is kind of stationary, it sort of looks the same from everywhere, then it's enough to show that there are no bi-infinite geodesics crossing through the origin. Yeah? Now, the way so this is what we'll try to exclude. And the way we go about it is we look at a big box of side size n, and we'd like to show that with high probability, so namely that with probability, well, that every geodesic starting anywhere from the south-west border and crossing and terminating in the northeast border of this box, the probability of it to cross the origin goes to 0 as n goes to infinity. Right. So this, to show this sort of can be broken into three cases. The first of which is where you assume that the geodesic is sort of close or stays very close to the axis. And in that case, what you show is that you want to show that if it stays too close to the axis, then it should converge to it should just agree with the axis itself, and then it becomes trivial, which we're not interested with. The second case is where you sort of come from a certain direction, as in this picture, you come from a certain direction and then you sort of break off into a different direction. What this would do is sort of generate this kind of a gap between the origin and the characteristic, the straight line connecting the two endpoints. And then you can show, for example, using the fact that you should stay close to the characteristic, that you can sort of rule out these cases. And finally, we're left with the most challenging part of the proof is to show that that this is the case where you have geodesics starting anywhere from here, not too close to the axis. They can have this kind of a random any direction, and then they stay close to the straight line connecting the two endpoints, the characteristic. Okay, so this is the one. This is like the more challenging one, and this is the one to which I'll try to sketch a proof in the next few slides. So right. So next, now that we know what we're trying to prove, what we're going to do is we're going to take the southwest boundary, okay, and we're going to break it into subintervals, so we're into the 2/3. And to each such subinterval, we're going to assign a patch on the northeast boundary that's larger than the interval itself, but it's sort of in the same direction. And we would like to show that the first step is to show that any geodesic, the geodesic starting anywhere in this subinterval and terminating in this big patch, with high probability will not cross the origin. Okay, so this is like the main issue now. So how do we show that? How do we sort of bound this event? So here you can see the two patches. There's the one here and the bigger one here. These U and V are 2 points. This U is any point in this interval, and V is any point on this patch here. And what we would like to do is sort of, first we divide the box into two rectangles, sort of that in the middle, we generate this kind of a ladder, okay? So this point here is the point, the origin, okay? We don't want to cross, so we want to show that with high probability, we do not cross. And this point is just taking a step to the right. So this is just 1, 0, the point 1, 0. And what the geodesic does, the geodesic is sort of trying to maximize things, right? To maximize the passage time. So what we would like to understand is its alternatives, right? We would like to, so we want to show that it doesn't cross through the origin, and so we have to understand its alternatives. We have to understand where would it like, what its preferences are. And so the way we do it is we sort of, we construct the different alternatives. The way we do it is for each 2 points, U and V, we generate, we look at the geodesic starting from you and terminating at the point here, at this point of the ladder. And then we walk across to the other side of the ladder, and we look at the geodesic starting from this point and terminating at the point here, okay? This is one option this is one path that the geodesic can take, right? This is two concatenated geodesics, and the geodesic can or might take that path, might not. So let's look at its alternatives. So if you go one step up, just one step up on the ladder, here on this side, you're going to see this kind of this positive increment. And the reason for that is this because going to this point, you can always go from this point and then go here. So this has to be sort of a positive, this has to be a positive gain going upward. On the other hand, here, using the same logic, you have a negative gain or a loss. And so we can sort of bookkeep this, and the overall cost is, for going one step upward, is you gain this and you lose this much. Okay, this is what happens when you go one step upward.
I have a question. I'm just not sure about exactly what you're showing us. So, is this column in the middle, the ladder, does it include new random variables, or you use the same and you only shift one side up?
So I didn't catch it. What did you say?
This column that you added in the middle, did you only shift shift the point that it comes in, or does this include new random variables that you inserted?
No, this is the lattice. This is the box where this is a straight line going through the origin, vertical line going through the origin, and this is just a vertical line going through 1, 0.
Okay. Yes. Okay.
So this is part of the box. I didn't add anything. No.
Okay.
This is part of the box. So right. So this is sort of one step. This shows you sort of what the alternatives for the geodesics, because maybe this should be noted that the geodesic has to cross through one of the steps of the ladder, right? So if we sort of understand its different alternatives on the ladder, then we should understand where it should cross. Right. So what does this mean? It means that we need to understand. So this is just one step on the ladder. But we can do this, we sort of do it again and again, going again up one step on the ladder, and this will sort of generate a random walk on the ladder. We will have two random walks, one going upward and one going downward on the ladder. And what we now understand is that the geodesic would prefer the path that gains the most weight, right? So if we go one step upward and we gain something positive, then it would rather go there than stay where it is, to stay put, right? And more generally on the upper ladder, it would want to cross wherever the maximum of this random walk is, right? And the same thing goes for the lower ladder. If you go downward, if you go one step down and you gain something, then you'd rather go there. If you don't, if you lose overall, then you'd rather stick where you are. But overall, you'd want to go where the maximum is. And the geodesic will actually cross between choosing the maximum between the argmax of these 2 points on the ladder. Right. So now the question is, what can we say about these random walks? So unless we can actually say something about this, then there's not much we can do about it. And Unfortunately, using something called the Busani functions, which I'm not going to go too much into in this talk, but maybe we can talk about it later. But this is a very powerful tool in this business. And what these Busani functions give you is that you can construct two other random walks, S up and S down. S up, both these new random walks will be dominated or are dominated by H up and H down, regardless of the two endpoints that you choose. So it doesn't matter which endpoint you choose on these two patches. These two random walks will dominate S up and S down. And what's nice about this thing is that we well understand the S up and S down. These are two IID random walks with a negative vanishing drift, and we know the distribution perfectly. We understand it perfectly. When I say a negative vanishing drift, what I mean is that if you scale this properly, then these random walks converge to a Brownian motion with a negative drift. This is what I mean by it. Right. So here you can see on this picture, going right is basically going up on the ladder. Okay, so we turn the ladder 90 degrees, and now this is going up on the ladder. H up is what you gain, this random walk. Okay, so just to recall in short, just to remind you that you start from here, and then you would want to go. We said you'd rather, the geodesic would rather go where it gains something, right? So it would probably not want to go one step to the right because it loses. But then if it goes further to the right, you can see that it has these these high mountains where it would like to go, right? It would rather go there than just stay here, right? Because it gains something. And the same thing goes for the lower ladder, right? If you go downward, and here this is kind of easy. That it would always want to go, not stay put and just travel to the left. The geodesic will always prefer going downward on the ladder than sticking to the origin. And then we see here the S up and S down. These are the two new random walks that we received, or we got from the Busani functions. And now, so to rule out, let's look at the upper ladder, okay? If you want to rule out that we stay at the origin, right? It's enough to show that H up has a non-negative, a positive maximum, right? This is enough, because if it has a positive maximum, the geodesic will prefer crossing there. So we can do this through S up, right? So we understand well S up, and the maximum of S up has to be smaller or equal than the maximum of H up. And so if we show that the maximum of S up with high probability is positive, then this would imply that you with high probability will not cross through the origin. Okay, so this boils down to the following. So the probability of S up and S down staying below zero, staying constantly negative, and this can be computed because we understand S up and S down well, and this can be computed to be n to minus 1/3, okay? And this is not enough, but this is not, the reason why it's not enough, first let me explain, is because here we sort of divide the southwest boundary into intervals of size n to the 2/3, and this means that you have n to the 1/3 many such intervals. And so if you use union bound, which is what you do when you don't know anything about the model, then this will be a constant, it would not go to zero. So this is why it's not enough. But then why is that the only thing we can say about this is that why is it n to the minus 1/3? This is just coming from S up, but unless we understand anything, unless we can say something about the way they're coupled, the S down and S up, we can't really say whether it's whether we can do anything better than. But it could be that they're coupled in such a way that when they're both negative at the same time, and then we can't really say anything better than n to the minus 1/3. But fortunately, using again these better knowledge of the Boozman functions coming from recent work by Fan and Zeppelin, then we can show that this is a bit of a miracle, but it turns out to be true that S up and S down are independent. Okay, and this, if you sort of get to know these models, everything is so dependent there, and decorrelate so slowly, and it's kind of a bit of a miracle that that they're sort of independent, S up and S down. And this allows us to push this bound even further and show that this is a big O of n minus 2/5. Okay, and now using this, we can do the following. Let me just. We can do the following. We just, again, we said we have n to the 1/3 many such intervals, regardless where the starting point and the end point, where the endpoints are in these two patches. We know that we can bound the probability of the geodesic crossing through the origin is n to the minus 2/5. And using union bound, we show that this goes to 0. Okay. Okay. So this is the sketch of the proof. If you have any questions. Okay. So now we move to the third part of the talk. Just a second. Where I'll discuss a closely related model. It's also in the KP's universality class, and it's called a random polymer. A random polymer on Z square. So again, we look at Z square, and we have again these IID random variables. Again, IID means that they're independent and they're identically distributed. And we take them to be positive. And then, again, we fix 2 points, X and Y, okay? And then again, we look at paths starting from X, terminating at Y, that take only either path to the right or paths upward, okay? Upright paths. And now, second. So now you can see such a path again. It's an upright path connecting X and Y. But here now what I did is I sort of, colored it so that the the tone of the color of the blue in this path is sort of proportional to the weight collected along itself. Okay, so this has a certain amount of weight, this path. But this path, as has a much darker tone to it, then this is sort of heavier, has more weight along itself, and this path that's brighter than the two previous ones is has the least weight of the three. Okay, and this is sort of what I would like to do. What we would like to do is sort of instead of sort of singling out the best, the path that attains the most weight, what we'll try to do is sort of give the different paths weight that's proportional to their contribution of the total weight of all upright paths connecting X and Y. So this is sort of a classical thing in statistical mechanics, and this is done through something called the Gibbs measure. And but it's basically what I just explained. So you first define something called the partition function between 2 points, between the points X and Y, which is just the amount of weight collected by all paths. Okay, so you just sum over the paths. This is just the state space of all paths starting at X and terminating at Y. And to each such path, you take here we take the product of the weights, okay, of the path. But this is just because of the what do you call it? Just the way, this is how Gibbs measures are done. So this is just, but it could be a summation as well. It's not that important. But we take the product, and then so given an environment, when we fix the environment, we no longer have this unique path, but we have a measure on paths. That's called the Gibbs measure, and it's basically the weight collected by a certain path divided by the total weight collected by all the paths. Okay? And here, this omega is just to sort of tell you that this is giving a certain environment, giving a realization of the weights on the lattice. Then what you can do is you can also sort of average over the environment, and you get something called the annealed measure, and this is another measure on paths. Okay? So as I often get confused by these by the two models, going from one model to the other, here is a cheat sheet. So this is all you need to remember, that for last passage percolation, this was gxy. This is the passage time. For polymers, this is the logarithm of the partition function, aka free energy. And more importantly, and basically this is what you should take from this slide, is that what was before geodesics, this unique path going from X to Y for last passage percolation, for the polymers is a measure on paths. Okay, this will be denoted by Q omega XY. Okay. Okay, so before you may have noticed that I assumed that we had, for last passage percolation, I assumed that the model had exponential random variables, that the distribution was exponential. And here too, I will have to assume that I have a certain distribution, and this would be the distribution of Y0, of the weight at the origin, or any other vertexes. This is a stationary measure. will be the inverse gamma distribution, given this is the density. And this model is called the log gamma polymer, okay? And this was shown by Sepalainen in kind of a seminal paper in 2009 to be exactly solvable. And what I mean by that, and this goes, the same goes for the exponential last passage percolations. These models are such that they give rise to these pre-limiting objects, exact expression for the pre-limiting objects. So if you recall the proof for the central limit, for example, for the classical central limit in the Gaussian case, then this was originally derived for the Bernoulli case, okay? And where they saw that the way they showed it is to just, they managed, before they took the limit, they managed to show that exactly what the central limit theory, what the fluctuations are. And then they took the limit and they saw these Gaussian, Gaussian distribution. Later, you have, now we're familiar with this sort of using the Fourier transform characteristic functions, but this is the way it started. So in a sense, this is where this kind of, this field is now at. We're at the place where we can only say things about these exactly solvable models, these models where we can get these exact expressions.
Ofer?
And
Ofer, may I ask a question?
Yes.
You defined, so what is the polymer? You defined a bunch of unknown variables, but I don't see the object.
So the observables we're interested in, well, for me, for this talk is this measure on paths. We would like to understand it. It's fluctuations, whether it exists. This is like, and also, so, okay, but generally, for the polymer, these are the two basic, most important observables. The free energy, you can ask this is a random thing, right? You can ask what is its fluctuations, does it have, actually I'm getting to it right now. And then you can ask the same thing about the distribution on the paths. You can ask, what does it look like? Is it concentrated along the characteristic line, right? You could have different paths, but do you have, is it mostly concentrated? All the path, the measure on the path concentrated along the straight line connecting the two endpoints, X and Y. So it's quite similar to these two, but is this?
This is a distribution on some big space, but where is the polymer? What do you mean by a polymer?
So okay. So a polymer is just, some people even called last passage, they don't call it the geodesic, they call it a polymer. A polymer is just the lines connecting the two endpoints. This is what it is. When you say a random polymer, you mean that it's not a geodesic. It's not. So here, given so the randomness in the name is regarding once you fix the environment. So if you fix the environment for last passage percolation, you get a deterministic one, right? You get a deterministic geodesic. Here it's random. You get a random polymer, a randomness upright path, if you will. Okay, so like in the previous model, we have here this law of large numbers. So if you scale the free energy, you converge to a certain number, which we know what it is. So it a bit depends on I didn't put it here because it depends on these parameters you choose, but we understand it well. Moreover, we understand the fluctuations. Again, these are a Tracy-Widden distribution. This shouldn't come as a surprise because there is a universal. This is part of the same universality class, so you should see the same macroscopic behavior of the fluctuations. And it turns out also that the random polymer is sort of concentrated, like the same way the geodesic was concentrated between the two endpoints. Then the measure itself is concentrated between the endpoints. How long do how much more do I have time? I can't hear you.
You have 5 minutes, but if you need more, please tell me how much time do you need?
Maybe a bit, okay, maybe just a slightly more than 5 minutes, but yeah, around that, okay, I'll try to make it quick. So what's the motivation behind this polymer, this random polymer? First is algebraic one, is that for the last passage percolation, you use the max plus algebra for making computations, and for the polymer, you get, because you have this multiplication, you have the plus product geometry algebra. This is called geometric lifting. And in some sense that I didn't discuss here, you can sort of approximate. You can approximate the last passage percolation by the random polymer. But working with plus product algebra is much easier than working with max plus. Depends who you ask, but for most people, I guess. The second motivation comes from stochastic partial differential equation, such as the Burger's equation. So there you can sort of understand better the solutions to these stochastic partial differential equations using the geodesic picture. So there's this something called the Feynman Katz representation of solutions, and you can use that to get the to understand better the solutions. And also you can think of this as a random walk in a random environment. So but maybe I'll just leave it at that because we don't have much time. So what is the analog? Okay, what is the analog for the polymer, for the random polymer? So again, we're moving from one specific path to a measure on paths, right? So if we have a measure on path, we need to define the state space of the path. So XU will just be all those paths starting from the point U, rooted at U, going to infinity, taking again only upright paths, upright steps. And a bi-infinite polymer just lives on this space. This is just a bi-infinite upright path. Okay, this is the state space for the measures. And now, what is the analog of the infinite rooted geodesic? This is the semi-infinite polymer Gibbs measure. This is a measure on paths, on the path, such that if you sort of restrict yourself to in between two strips, such as here, and you condition on anything that's outside that strip, then inside you will have the quench distribution that we defined. Okay, so this is like saying that if a geodesic is, if you fix 2 points, then in between it's a geodesic. So this is sort of similar. And the main result in this area is that from Janjinian and Osulaga, and it says that with probability 1, you should have there is a semi-infinite Gibbs measure, okay, and it's also directed in a sense that you sort of have direction as you had with the infinite geodesics of last passage percolation. So basically what it means is existence and uniqueness of these measures. And now you can define also a bi-infinite polymer Gibbs measures. Again, this is a distribution on infinite paths. Check a strip, condition on outside the strip. The behavior inside the strip will be that of the Gibbs measure between 2 points. Okay, And so now the question is, are there bi-infinite polymer Gibbs measures? And this is joint with Timo Seppäläinen, where we show that for the log gamma polymer with probability 1, every bi-infinite Gibbs measure is supported on straight line. Namely, there are no non-trivial Gibbs measures. Okay, so this is any questions about this result? I went a bit fast towards the end, but I hope it's not at the cost of this clarity. So finally, just to wrap things up, for exponential last passage percolation and the low gamma polymer, we showed that there are no bi-infinite geodesics or Gibbs measures. What is still open is, and this is the holy grail of this business, is first passage percolation. There are many results around it. There's actually there's a talk by Chris Hoffman today, if you're interested, where he's supposed to tell, there's new results on this, on bi-infinite. I'm not sure if he proved the whole thing, but probably got closer to this question, showing non-existence of bi-infinite geodesics in first passage percolation. And in last passage percolation, what's still open and for polymers is general weights. So that's also seems to be hard, maybe as hard as the first passage percolation. That's it. Thank you very much.
Thank you, Ofer. Let's thank the speaker. Any questions to the speaker? Comments?
So on first passage percolation, when you say, you mean general weights or just the exponential? When you, so that this is the bi-infinite geodesic is open.
For first, well, you ask for first passage?
First passage.
So first passage, there's no distinction between the exponential is as hard as anyone, as any other weights distribution. So this is the problem with so there's no, it's not exactly solvable, this first passage. We don't have these nice, regardless of the choice of the distribution of the weights. So we don't really, so everything is hard in first passage. There are no easy, nothing is, everything is super hard. Yeah, that's why much is less known about these models.
More questions? Well, if not, let's thank the speaker again. And